Welcome, drift in and make yourself comfortable. As you settle in and allow the noise of the day to soften around you, I invite you to drift with me into a quieter place. A place where curiosity moves slowly and the universe reveals itself one gentle layer at a time. Whether you're here to fall asleep or to disappear into a moment of peaceful wonder, you're in the perfect place. The cosmos has a way of comforting us, reminding us that even in its vastness, there is order, rhythm, and a deep, steady calm. Tonight, we begin a journey into the invisible structure of the universe, a landscape shaped by forces older than stars, older than galaxies, older even than light itself. This is the quiet domain of dark matter, the unseen foundation holding the cosmos together. Though invisible, its presence is everywhere. Every galaxy, every filament, every cluster is shaped by the soft gravity of dark matter. And in this story, we move slowly through that hidden architecture, following the subtle patterns that govern the sky. You don't need any background in physics or astronomy, just an open mind and a comfortable place to lie back. I'll guide you through each idea at a gentle pace, with simple explanations and soft transitions. Together, we'll explore the grand structures of the universe, but always in a way that soothes rather than overwhelms. Think of this as a quiet conversation under a tranquil night sky where every concept unfolds like a drifting cloud. As you listen, notice how your breath naturally slows. Notice how your shoulders loosen. The universe asks nothing of you here. There is no urgency in cosmic time, no deadlines, no noise, only slow expansion, gentle motion, and the restful reassurance that everything, every cluster, every star, every grain. In tonight's exploration, we'll start at the largest scales imaginable, the cosmic web. This enormous structure spans billions of light years and forms the backbone of the universe. We'll look at how dark matter sculpted this web, how galaxies trace its filaments, and how quiet gravitational influences guide the growth of clusters and superclusters. As we move through these ideas, the goal isn't to memorize anything or solve any mysteries, it's simply to feel the calm of understanding, light, steady, and spacious. So take a moment to get comfortable. Let the bed or the couch or the warm place beneath you hold your weight. Let your mind drift outward, away from today's concerns and into the soft darkness of intergalactic space. Out here, everything moves slowly, gracefully, as if the universe itself were breathing. Welcome to this journey. Welcome to the quiet frontier of the cosmos, and welcome to Sleepy Cosmos. If you enjoy these quiet journeys through the cosmos, you can gently tap the subscribe button and like the video. It helps the channel grow and lets me know you'd like more stories like this. And before you drift too far into sleep, feel free to leave a comment and tell me what time it is where you're watching from. I love seeing how many corners of the world we explore the universe from together. Chapter 1. A Universe. Wrapped in mystery. Dark matter entered modern astronomy not as a dramatic discovery, but as a quiet problem that refused to go away. When astronomers first mapped how galaxies move, they expected the motions to follow the same simple rules that describe planets orbiting the Sun. Closer objects should move faster, and distant ones should slow down. Instead, the data told a different story. Stars far from the centres of galaxies, that something did not appear in any photograph, any spectrum, or any catalogue of stars. It was as if the universe were whispering that most of its mass was hiding in plain sight. To appreciate why this is so striking, it helps to think about how gravity normally behaves. In our solar system, almost all the mass is in the Sun. Planets that orbit close to the Sun, like Mercury, feel a stronger gravitational pull and move very quickly. Farther out, where the pull is weaker, planets like Neptune and Pluto move more slowly. If you plot their orbital speeds against distance, you get a curve that slopes downward. Astronomers expected something similar for stars orbiting the centres of galaxies. Yet when they measured those speeds with careful spectroscopy, the curve flattened out instead of dropping. The outer stars were moving just as fast as the inner ones. According to the visible mass alone, that should not be possible. Either the law of gravity was wrong on galactic scales, or there was more mass present than met the eye. For a while, both possibilities were explored seriously. Some physicists proposed alternatives to Newtonian gravity, trying to adjust the equations so that galaxies could rotate rapidly without flying apart. Others took the mass discrepancy at face value and suggested that galaxies might be embedded in halos of invisible matter. Over the decades, as more measurements accumulated, the extra mass explanation quietly gained the advantage. The idea that galaxies sit inside enormous halos of unseen material became not just convenient, but necessary. These halos are now understood to be much larger than the visible parts of galaxies. When you look at a spiral galaxy, you see a bright disk of stars, perhaps some gas glowing in emission, and a dense bulge in the centre. That luminous structure is only the tip of a far larger distribution of mass. The dark halo is thought to extend several times farther than the visible edge of the disk, forming an almost spherical region of influence. If you could see it, the galaxy would look less like a thin pinwheel and more like a small glowing disk nested inside a vast transparent cloud. It is the gravity of this halo that keeps the outer stars in their fast orbits, preventing them from drifting away into intergalactic space. Dark matter's invisibility is not just a poetic phrase. Ordinary matter, atoms, electrons, ions, interacts with light in many ways. It emits radiation when it's hot, absorbs photons passing through it, and scatters light into different directions. That is why gas clouds glow, why dust lanes appear as dark streaks, and why stars shine with different colours. Dark matter, by contrast, seems almost completely indifferent to light. It does not glow at any wavelength we can detect. It does not cast obvious shadows. It does not absorb, scatter, or reflect photons in a way that leaves a clear signature in our instruments. As far as we can tell, it interacts primarily through gravity, tugging on other matter while remaining electromagnetically silent. If something cannot be seen directly, how can we map it? Astronomers rely on the way mass influences both motion and the path of light. One of the most powerful tools is gravitational lensing. According to general relativity, mass curves space-time and light follows the curved geometry. When a massive object lies between us and a more distant galaxy, it can bend and distort the distant galaxy's light, much like a glass lens distorts the appearance of objects seen through it. Sometimes the effect is subtle, producing small shifts in shape and orientation. In more extreme cases, it can stretch a single galaxy. By studying these distortions statistically, astronomers can reconstruct how mass is distributed, including mass that does not emit light. These reconstructions have revealed something remarkable. The pattern of lensing around galaxy clusters and large-scale structures almost always indicates more mass than is visible in stars and gas. When the distribution of dark matter is inferred from lensing, it often forms extended halos and filaments that line up with, but go far beyond, the luminous components. A particularly famous example is the Bullet cluster, where two clusters of galaxies have collided. In that system, the hot gas slowed down and piled up due to collisions, while the inferred dark matter components pass through each other relatively unimpeded. The separation between where the light is and where the gravitational mass appears to be strongly suggests the existence of a non-luminous component. Dark matter is not only important for the way individual galaxies behave, it also shapes the universe on its larger scales. In the early universe, shortly after the Big Bang, matter and radiation were tightly coupled. Photons scattered frequently off charged particles, resisting any attempt of ordinary matter to clump under its own gravity. Dark matter, however, does not feel electromagnetic forces. It begins to collapse into overdense regions earlier, forming the first gravitational wells in the expanding universe. Later, when the universe cools and neutral atoms form, ordinary matter can finally fall into those wells, amplifying the tiny initial fluctuations into the galaxies and clusters we see today. Simulations of cosmic structure formation make this role vivid. When cosmologists run numerical models that include dark matter, dark energy, and ordinary matter, starting from a nearly uniform early long filaments form, intersecting at dense nodes where clusters of galaxies develop. Between the filaments lie vast voids with relatively little matter. When the results are compared to large galaxy surveys, where millions of galaxies have been mapped in 3 dimensions, the agreement is striking. The observed universe really does resemble a cosmic web, and dark matter provides its underlying skeleton. Despite this impressive indirect evidence, the microphysical nature of dark matter remains unknown. The most widely studied hypothesis is that dark matter consists of a new kind of particle that rarely interacts with ordinary matter. Candidates include weakly interacting massive particles, sometimes called WIMPs, and lighter candidates such as axions. Experiments on Earth attempt to detect these particles either by observing rare collisions in highly shielded detectors or by creating them in high-energy collisions in particle accelerators. So far, no clear signal has emerged. Each null result constrains the properties that dark matter particles could have, narrowing the range of possibilities but not yet revealing the answer. There are also alternative approaches that keep the focus on gravity itself. Some theorists have proposed that our understanding of gravity breaks down at very low accelerations or on galactic scales, and that what we interpret as missing mass might instead be a sign that the law of gravity needs to be modified. These modified gravity theories can sometimes reproduce galactic rotation curves without invoking dark matter, but they usually face difficulties when applied to clusters, lensing, and the cosmic microwave background all at once. While the debate is scientifically healthy, the simplest way to fit all available data consistently still involves a dominant unseen mass component. For someone listening in the dark trying to relax, there is something quietly reassuring about this picture. It is held together by deep, underlying structures that do not demand our attention but are always present. Dark matter plays the role of a stabilizing background, a kind of gravitational framework within which the bright parts of the universe can form, evolve, and sometimes even expire. The galaxies we see are like lights strung along invisible scaffolding. The scaffolding itself is not dramatic to the senses, but without it, the lights would never have been arranged in such intricate patterns. It is also humbling to realize how small a fraction of the universe our senses can access. All the stars visible to the naked eye, all the glowing gas clouds captured by telescopes, and all the familiar atoms that make up planets, people, and everyday materials together account for only a minor share of the cosmic energy budget. The rest is dominated by dark matter and dark energy, components that reveal themselves only through their gravitational imprint and their role in cosmic expansion. Rather than feeling unsettling, this can be experienced as an invitation to a broader perspective. Reality is richer and more layered than first impressions suggest. As you drift towards sleep, you can imagine dark matter as a calm, pervasive presence, diffused through the universe like a silent field. It does not flash or flicker. It does not erupt in bursts or collapse into bright flares. It simply sustains the structures that give the universe its large-scale form. Galaxies orbit within halos of it. Clusters gather where it is densest. Filaments of it thread the gaps between visible structures. Even here, in the quiet room where you lie, the Milky Way's dark halo is gently shaping the motion of our solar system around the galactic center. There is no need, tonight, to solve the mystery of what dark matter is made of. That question drives the daily work of many researchers, but for now it can remain open. What matters in this moment is the feeling of living in a universe that is coherent, structured, and supported by hidden layers. Dark matter is a reminder that not everything important must be obvious or bright. Some of the most essential ingredients of reality operate quietly in the background, providing stability while remaining almost entirely unseen. In the next chapters, we will move deeper into this subject, tracing how dark matter halos are measured, how they influence the evolution of galaxies over cosmic time, and what the leading theories suggest about its fundamental nature. For now, it is enough to rest with the idea that almost every galaxy, including our own, is cradled in a vast invisible halo. The stars may be the most eye-catching part of the universe, but they are not the whole story. Beneath their light, an unseen mass holds everything together, creating a cosmic environment where, as your thoughts slow and your breathing becomes more regular, you can let this image settle in your mind. Countless galaxies scattered across a deep, silent cosmos, each one wrapped in a halo of dark matter. They move, merge, and evolve within this invisible framework, carrying their stars, planets, and possible life along with them. It is a universe both mysterious and reassuring, governed by laws that we are gradually uncovering, supported by components that we cannot yet fully explain. In that blend of knowledge and uncertainty, there is space to relax, to wonder, and to drift gently into sleep. Chapter 2. Clues. Hidden in the motion of galaxies. Dark matter did not enter scientific conversation through a single dramatic experiment, but through a slow accumulation of discrepancies, small mismatches between expectation and observation that gradually formed. This chapter explores how those first clues emerged, why they mattered, and how they reshaped our understanding of the universe. The tone here remains calm, deliberate, and sleep-friendly, even as we examine the scientific reasoning behind the earliest evidence for dark matter's existence. Astronomers in the early 20th century were beginning to map the motions of galaxies with greater precision. These motions were not random. They were governed by gravity, and gravity in turn was governed by mass. When astronomers measured the velocities of galaxies within clusters, they found that these galaxies were moving far too quickly to be held together by the visible mass alone. The clusters should have dispersed long ago. Instead, they remained intact. This discrepancy hinted at the presence of additional mass that did not emit light, mass that was invisible to telescopes. Fritz Zwicky, a Swiss astronomer working in the 1930s, was among the first to point this out. He studied the Coma cluster, a dense region containing thousands of galaxies, and measured how rapidly those galaxies were moving. Using the virial theorem, a principle in classical mechanics that relates the average kinetic energy of a system to its gravitational binding energy, Zwicky calculated how much mass the cluster should have. The result did not match the amount of mass inferred from the light emitted by the galaxies. There had to be more matter present. Zwicky called this missing mass dunkle materie, dark matter. At the time, few took his claim seriously. The methods were new, the uncertainties large, and Zwicky himself had a reputation for bold statements. Yet the data remained. Something was holding galaxy clusters together. That something was invisible, yet it behaved like matter. It had gravitational effects but did not shine. It was as though the universe had hidden a large fraction of its mass behind a veil. As the decades progressed, technology improved. Telescopes became more precise, detectors more sensitive, and observational catalogues more complete. One of the most important lines of evidence came from the study of galaxy rotation curves. When astronomers measured how fast stars and gas clouds orbited the centers of spiral galaxies, they discovered that the outer regions were moving far more quickly than expected. According to Newtonian gravity, orbital speed should drop with distance if most of the mass is concentrated in the center. Instead, the speeds remained nearly constant. This flattening of rotation curves was not a minor anomaly. It appeared again and again in galaxy after galaxy. The implication was clear. Either the laws of gravity behaved differently at large scales, or galaxies contained far more mass than could be accounted for by their luminous components. Most astronomers concluded that the latter explanation was more plausible. It required only that there exist a new, invisible. The alternative demanded rewriting the foundational laws of physics. The consistency of rotation curves across many galaxies strengthened the case. Spiral galaxies of various sizes and compositions all showed the same pattern. Outer stars moved too quickly to be held in place by visible mass alone. These observations implied that galaxies were embedded in large halos of dark matter, halos that extended well beyond the luminous disk. Without these halos, galaxies could not maintain their structure over cosmic timescales. Another line of evidence came from gravitational lensing. According to general relativity, massive objects bend the path of light. When light from a distant galaxy passes near a massive foreground cluster, the image of the background galaxy becomes distorted. By analysing these distortions, astronomers can map how mass is distributed, even if that mass does not emit light. Gravitational lensing revealed massive structures that far exceeded the amount of visible matter. These maps showed that dark matter was not evenly distributed but clumped in ways that matched simulations of large-scale cosmology. Cluster collisions provided even more dramatic clues. The Bullet cluster, a pair of galaxy clusters that collided at high speed, offered especially compelling evidence. During the collision, the hot gas, composed of ordinary matter, slowed down due to friction, piling up in the center. Dark matter, by contrast, passed through largely unaffected. Using gravitational lensing, astronomers could map where the mass was located. The result was striking. The mass was concentrated where the galaxies had passed through, not where the gas had slowed. This separation between luminous matter and gravitational mass provided clear, visual evidence that dark matter exists as an independent component, not simply an artifact of modified gravity. In the calm space between these discoveries, rotation curves show that galaxies are heavier than they appear. Velocity measurements in clusters reveal that many systems contain far more mass than their light suggests. Gravitational lensing shows exactly where that mass resides, even when no luminous matter is present. Cluster collisions demonstrate that dark matter can behave differently from ordinary matter, passing through itself and other structures with minimal interaction. For someone drifting towards sleep, this slow accumulation of evidence can feel soothing. Science is often portrayed as a series of eureka moments, but the reality is more gradual. It is a patient process of collecting data, comparing predictions, and refining theories. Dark matter exemplifies this process. It is not a discovery born of a single observation, but of many small clues aligning over time. Each observation adds another thread to a growing tapestry. Understanding dark matter also encourages humility. It reminds us that our senses are limited. We see only a small fraction of the universe's contents. The stars and galaxies that light the sky are like decorations on the surface of a vast invisible structure. Dark matter forms the foundation on which these luminous objects rest. Without it, galaxies would not hold together, clusters would not form, and the large-scale structure of the universe would look profoundly different. The fact that dark matter is invisible does not make it unknowable. Scientists use its gravitational effects as a guide, tracing the contours of the unseen. These methods reveal a universe filled with intricate distributions of mass, extending across billions of light-years. Dark matter forms the cosmic framework, the scaffolding within which galaxies take shape. Even though we cannot observe it directly, we can measure its influence with remarkable precision. As this chapter approaches its close, imagine the early astronomers observing distant galaxies, measuring their velocities, and noticing discrepancies that would later reshape cosmology. Picture the slow evolution of ideas, the refinement of measurements, and the emergence of a new concept that challenged the boundaries of knowledge. Dark matter began as a quiet whisper in the data, a subtle hint that something was missing. Over time, those whispers grew into a confident statement. Most of the universe's mass is invisible. The clues were always there, hidden in the motions of galaxies, in the distortions of distant light, and in the structure of cosmic clusters. All that was needed was the patience to listen, to measure carefully, and to follow the evidence wherever it led. In this quiet persistence, there is a lesson worth carrying into the night, that understanding often arrives gradually, through small insights that accumulate into clarity. As you settle deeper into rest, let the story of these early clues become a gentle reminder that discovery is a process, not a moment. The universe does not reveal its secrets all at once. It offers hints, patterns, and subtle signals that reward those who approach with curiosity and calm. Dark matter is one such secret, still unfolding, still teaching us that even the unseen can shape the cosmos in profound and beautiful ways. The search for dark matter continued to push astronomers into new methods and new questions. One of the most informative tools came from observations of the cosmic microwave background, the afterglow of the Big Bang. This faint radiation, spread almost uniformly across the sky, contains tiny fluctuations that encode information about the early universe. By studying the precise patterns of these fluctuations, scientists can determine how much ordinary matter, dark matter, and dark energy exist. The results consistently show that dark matter makes up a much larger portion of the universe's mass than anything made of atoms. These findings support the picture that dark matter played a central role in shaping the gravitational environment in which galaxies formed. Further measurements from large galaxy surveys reveal how galaxies cluster together across vast distances. The way galaxies group and separate over hundreds of millions of light-years matches the predictions of models that include dark matter as the dominant mass component. Without dark matter, the observed large-scale patterns would look very different. These surveys, which map the positions of millions of galaxies, offer a panoramic view of the cosmic web, and within that web the influence of dark matter is unmistakable. Though these discoveries emerged gradually, they paint a consistent picture. Dark matter pervades the universe, shaping the large-scale structure and influencing the motions of galaxies and clusters. Even though it remains elusive in direct detection experiments, its gravitational signature appears everywhere astronomers look. This brings us back to the early evidence, the rotation curves, the velocity measurements, and the gravitational lensing observations. Each clue enriched the understanding of what dark matter must be doing at cosmic scales. Together, they form a foundation that modern cosmology rests upon. The universe is not simply a collection of stars shining in the void, but a dynamic structure shaped by forces both seen and unseen. As you drift deeper into rest, consider how these early clues emerge from careful observation and persistent curiosity. The astronomers who first noticed these patterns did not set out to discover dark matter, but simply to understand the galaxies and clusters they were studying. In doing so, they uncovered something far more profound, a reminder that the universe often holds surprises for those who take the time to look closely. Let this story guide you into the night with a sense of calm and wonder. The cosmos is vast, but it is also coherent, governed by laws that can be discovered and understood. Even the invisible parts of the universe fit into this structure, shaping the night sky in ways that invite reflection and rest. These insights also reveal how interconnected the universe truly is. The motions of stars within a single galaxy, the clustering of galaxies across cosmic distances, and the faint echoes of the early universe all point toward the same conclusion. Dark matter is essential to the cosmos. It provides the framework upon which visible structures form and evolve. Understanding its role not only deepens scientific knowledge, the patterns we observe today were shaped billions of years ago by forces still at work, guiding the evolution of the universe with steady, invisible hands. Chapter 3: The Formation of Dark Matter. Halos. Dark matter halos are among the most important structures in cosmology, yet they are invisible to the eye and detectable only through their gravitational influence. A halo is not a rigid shell or a sharply defined sphere. It is a diffuse, extended region where dark matter has collapsed under its own gravity, forming the gravitational backbone of a galaxy or cluster. For someone drifting into a calm, contemplative state, the idea of halos provides a comforting sense of order. These invisible structures are stable, ancient, and quietly influential, shaping the evolution of galaxies over billions of years. Understanding how halos form requires tracing the history of matter back to shortly after the Big Bang. The universe was remarkably uniform, with only slight variations in density. These tiny irregularities were enough for gravity to gain a foothold. Dark matter, unaffected by radiation, began to accumulate in regions that were just slightly denser than their surroundings. Over time, these overdense regions grew more pronounced as they pulled in additional dark matter from their environments. This process, known as gravitational collapse, occurred on many scales simultaneously. Small halos formed first, and larger ones gradually emerged through mergers and continuous accretion. In this way, halos built themselves from the bottom up, accumulating mass quietly but steadily. As halos grew, they developed internal structures shaped by the motions of dark matter particles. Unlike ordinary matter, dark matter does not cool by emitting radiation, so it cannot collapse into disks or dense clumps. Instead, it forms spheroidal distributions with densities that peak toward the center and gradually taper off with distance. Simulations reveal a consistent pattern. The density increases sharply near the core, creating a cusp, while the outer regions are extended and gentle. This structural profile is not imposed by any fundamental law, but emerges naturally from the physics of collisionless matter evolving under gravity. One striking feature of halos is their resilience. Because dark matter interacts only weakly, halos can pass through each other without being destroyed. Ordinary matter, by contrast, can collide, heat up, and slow down during galactic encounters. This difference becomes clear in observations of colliding clusters, where the dark matter components sail through nearly unimpeded. This resilience ensures that halos persist for billions of years, maintaining their identities even as galaxies merge, reshape themselves, and evolve. Halos also grow through mergers. In the early universe, small halos formed first, and over cosmic time they collided and combined to create larger structures. These mergers are often violent events on astronomical scales, but because dark matter does not radiate energy, the merged halo quickly settles into a new equilibrium. The resulting structure retains imprints of its formation history in subtle ways, such as variations in density or the presence of subhalos, smaller halos embedded within larger ones. These subhalos act like fossils, preserving clues about earlier stages of cosmic evolution. Subhalos are particularly interesting for their role in shaping galaxies. When a large halo forms, it does not fully erase the smaller halos that merge to create it. Many of these smaller structures survive as distinct entities orbiting within the parent halo. In the Milky Way's halo, for example, these subhalos may correspond to dwarf galaxies, or even to smaller clumps that can. Their distribution offers valuable information about how dark matter behaves, providing constraints on its particle properties and interactions. As dark matter halos form, they create gravitational wells into which ordinary matter falls. Gas cools, condenses, and eventually forms stars and galaxies. The shape of the visible galaxy is therefore determined by the shape of the underlying halo. Spiral galaxies tend to form in halos with high angular momentum, where the gas can settle into a rotating disk. Elliptical galaxies, on the other hand, are often the products of mergers that stir the gas and stars into more disordered motions. In all cases, the halo provides the gravitational stability needed to maintain coherence over long periods. Simulations of halo formation reveal the elegance of this process. Starting from nearly uniform initial conditions, the universe evolves into a web-like pattern dominated by dark matter. Halos form at the intersections of filaments, while voids appear where matter is sparse. These simulations match observations remarkably well. When astronomers map the distribution of galaxies in large surveys, they find the same filamentary structures, the same clustering tendencies, and the same large-scale geometry predicted by dark matter models. The agreement is a strong indicator that halos are not just mathematical constructs, but real components of the universe's architecture. One of the most intriguing aspects of halos is their universality. Across a vast range of masses, from small dwarf galaxy halos to massive cluster halos, the density profiles follow similar patterns. This suggests that despite variations in environment, history, and scale, the formation of halos is governed by simple gravitational principles. This universality offers a soothing sense of coherence. No matter where one looks in the cosmos, the same underlying structures appear, shaped by the same quiet processes. In the centers of halos, where densities are highest, lies a puzzle. Simulations often predict steep density cusps, while some observations suggest flatter cores. This discrepancy, known as the cusp core problem, remains an active area of research. Some scientists propose that interactions between dark matter and baryons could flatten the core. Others suggest that the nature of dark matter particles themselves may lead to different inner density structures. This tension between theory and observation is not a source of frustration, but a sign that the universe still holds deeper mysteries waiting to be explored. As you drift into a calmer state, imagine a dark matter halo not as a dense object, but as a vast, diffuse field. It stretches beyond the visible galaxy, enveloping it in a protective cocoon of gravitational influence. The stars you see are just the brightly lit decorations suspended within this structure. Beyond them lies a sea of unseen mass, shaping the galaxy's destiny with patient and quiet persistence. The halo neither demands attention nor reveals itself directly, yet it provides the framework for everything that shines. In this chapter, we've explored how halos arise from the initial conditions of the early universe, how they grow through mergers and accretion, and how they guide the formation of galaxies. These structures are the foundation on which cosmic architecture rests. Their quiet presence is a reminder that much of the universe operates behind the scenes, shaping the visible world without seeking acknowledgement. As you prepare for rest, let the idea the universe is supported by structures both seen and unseen, and within that balance lies a sense of calm and wonder. Another essential aspect of halo formation is the role played by cosmic expansion. As the universe expands, regions of slightly higher density resist that expansion more effectively than their surroundings. Dark matter, being cold and slow-moving in most models, sinks into these regions and enhances the gravitational potential. This enhanced potential allows halos to gather more mass over time, creating a runaway effect. Larger halos grow faster, pulling in material from greater distances. This growth paid. The boundary of a halo is not a sharp line, but a conceptual surface known as the virial radius. Within this radius, the system is gravitationally bound and roughly in equilibrium. Outside it, matter still flows inward, especially along filaments. This structure reflects a balance between collapse and expansion, regions where gravity has gained the upper hand and regions where cosmic expansion still dominates. Thinking about halos in this way creates a calming sense of balance, a reminder that even the universe. Observations of satellite galaxies orbiting the Milky Way provide additional clues about halo structure. These satellites trace the gravitational field of the Milky Way's halo, revealing its shape, mass distribution, and extent. Some satellites follow elongated orbits that stretch into the distant outskirts of the halo, while others move in more circular patterns. Each orbit tells a story about the invisible landscape they traverse, offering further evidence that the halo is vast, structured, and dynamic. On even larger scales, halos participate in a process called hierarchical clustering. Small halos merge to form medium-sized ones, which merge to form larger ones. This bottom-up pattern is a central prediction of cold, dark matter models. The fact that observations align with this prediction gives cosmologists strong confidence in the general framework. Yet, uncertainties remain. Some dwarf galaxies appear to contain fewer subhalos than simulations predict, raising questions about the nature of small scale. All of these details contribute to a more nuanced picture of halos. They are not static or uniform, but living structures that grow, change, and interact over billions of years. They respond to their environments, to mergers, and to the gravitational tides of nearby halos. In some cases, halos can even be stripped of their outer layers during close encounters, revealing substructures and altering the trajectories of embedded galaxies. Despite these interactions, halos retain their essential identity, a ma. As we consider halos from a more philosophical angle, their presence they operate quietly, shaping galaxies without turbulence or radiance. Their influence is stable, extending across cosmic epochs. For the mind preparing for rest, halos represent the idea that structure can arise naturally out of simplicity, a gravitational response to small variations in density. The universe, rather than being chaotic or unpredictable, builds complexity from gentle beginnings. Halos embody that process, forming from tiny fluctuations and growing into vast, elegant structures that support galaxies and clusters. Future observations will continue to sharpen our understanding of these halos. Next-generation telescopes will map dark matter distributions with unprecedented resolution, using gravitational lensing, galaxy motions, and subtle distortions in the cosmic microwave background. Each new dataset will refine the details of halo formation, revealing even more about how the invisible scaffolding of the universe evolved. Yet the general picture is already clear. Halos are essential, enduring, and universal. They shape the cosmos in ways that resonate with anyone who finds comfort in order, elegance, and quiet stability. As you settle into deeper calm, imagine floating at the edge of a massive dark matter halo. Below you lies a galaxy, its stars orbiting gracefully, each motion a response to the halo's steady gravitational pull. Beyond that galaxy lie countless others, each wrapped in its own invisible cocoon, drifting through the cosmic web. The halos themselves do not shine, but their presence is undeniable. In their quiet gravity, you may find a soothing reminder of the deeper structures that hold the universe together. Chapter 4: Mapping the Invisible Universe. Mapping dark matter is one of the most profound achievements in modern cosmology. Unlike stars, gas, or dust, it leaves no spectral fingerprint, no glowing nebula, no silhouette against the sky. Yet astronomers have learned to trace its presence with remarkable precision. The key lies in understanding how gravity shapes not only the motions of galaxies, but also the path that light itself takes as it travels through the universe. For someone seeking a calm, intellectually steady narrative, the techniques used to map dark matter offer a unique blend of subtlety, creativity, and quiet scientific confidence. They reveal that even the unseen can be charted, provided one understands the right clues. The foundation of all dark matter maps begins with gravitational lensing. According to Einstein's general theory of relativity, mass warps the geometry of space-time, causing light to follow curved paths. When a distant galaxy's light passes near a massive object, such as a cluster of galaxies or a dense region of dark matter, astronomers measure these distortions, called shear, across large regions of the sky. Although the effect on any single galaxy is small, the combined distortions of thousands or millions of galaxies form a coherent pattern. That pattern reveals how mass is distributed, regardless of whether that mass emits light or remains invisible. This technique, known as weak gravitational lensing, has become one of the most powerful tools for mapping dark matter. Weak lensing surveys require deep, wide-field imaging and extremely careful statistical analysis. Individual galaxies have their own shapes and orientations, so astronomers must detect the tiny extra distortion caused by intervening mass. This involves averaging over immense numbers of galaxies and correcting for instrumental effects such as atmospheric blurring, telescope optics, and detector imperfections. Despite these challenges, modern surveys like the Dark Energy Survey and the Hypersuprime CAM project have produced high-resolution maps of dark matter spanning hundreds of millions of light-years. These maps show vast filaments stretching across cosmic space, with dense nodes where clusters of galaxies reside. The resulting image is a portrait of the universe's scaffolding, elegant, intricate, and entirely invisible to traditional telescopes. Strong gravitational lensing provides a more dramatic example of how light reveals mass. When a massive object lies almost exactly along the line of sight to a distant galaxy, the distorted image can form arcs, rings, or even multiple copies of the same background galaxy. These striking features are rare but powerful. They allow astronomers to measure the mass distribution of the lensing object with exquisite precision. In some cases, strong lensing has revealed substructures within halos that do not correspond to visible satellites, suggesting the presence of small, dark clumps of matter. These observations test theories of dark matter at galactic scales, providing a laboratory for exploring the properties of the invisible. Beyond lensing, the cosmic microwave background (CMB) offers another window into mapping dark matter. The CMB is the oldest light in the universe, a faint afterglow of the Big Bang. As this light travels through cosmic structures on its journey to Earth, its path is deflected by gravitational potentials. This effect, known as CMB lensing, creates a subtle pattern in the temperature and polarization maps measured by satellites such as Planck. By analyzing these patterns, cosmologists can trace the distribution of dark matter across the entire observable universe. CMB lensing is particularly valuable because it samples mass along a very long line of sight, providing a three-dimensional view of large-scale structure. Another approach involves tracing the motions of galaxies. Since galaxies move under the influence of gravity, their velocities contain information about the underlying mass distribution. In galaxy clusters, for example, astronomers measure how fast individual galaxies are moving relative to the cluster's center. The random motions of these galaxies indicate how much mass the cluster must have to hold them together. When compared with the mass inferred from visible matter alone, the results consistently reveal that dark matter dominates. These kinematic methods complement lensing, providing independent confirmation of the same structures. Large-scale redshift surveys extend the mapping efforts even further. By measuring the redshifts of millions of galaxies, astronomers can determine their distances and build three-dimensional maps of the cosmos. These maps reveal how galaxies cluster and how voids, filaments, and walls form across space. The patterns match the predictions of models that include dark matter as the dominant mass component. In particular, the statistical distribution of galaxy clustering, known as the two-point correlation function, traces the imprint of dark matter on cosmic structure. These maps, stretching across billions of light-years, offer a grand perspective on the invisible architecture guiding the formation of galaxies. Some of the most fascinating dark matter maps come from studying cluster collisions. When two galaxy clusters collide, their visible components, primarily hot gas, interact strongly and slow down. Dark matter, unaffected by pressure, this separation between visible and invisible components creates a natural experiment for mapping dark matter. The Bullet cluster is the most famous example, but several others have been discovered since. These systems provide some of the most direct evidence that dark matter behaves differently from ordinary matter, reinforcing the idea that it is a separate, non-luminous component. As mapping techniques improve, astronomers have begun to study smaller-scale dark matter structures. Subhalos, tiny concentrations of dark matter that orbit within larger halos, can sometimes be inferred through their gravitational effects on stars or on strongly lensed images. Detecting these small structures is crucial for testing different theories of dark matter. Some models predict a large number of subhalos, while others predict far fewer. The number, mapping these structures is challenging, but ongoing surveys continue to push the limits of what can be detected. All these approaches, weak lensing, strong lensing, CMB lensing, kinematic measurements, and galaxy surveys, contribute to a steadily improving map of the invisible universe. The resulting picture is remarkably consistent. Dark matter forms a vast cosmic web, with galaxies and clusters sitting at the intersections. The visible universe is a thin layer resting atop this deeper structure. For someone drifting towards sleep, this idea can feel grounding. It suggests that beneath the changing, shimmering lights of the sky lies a stable, pervasive framework, quietly shaping the cosmos without demanding our attention. As the chapter draws to a close, consider the elegance of these mapping techniques. They rely not on direct detection, but on inference, on reading the subtle signatures left by gravity. In this sense, mapping dark matter is as much an intellectual art as it is a scientific process. It requires patience, precision, and a willingness to look beyond the obvious. Yet the reward is immense, a deeper understanding of the universe's hidden structure, and a sense that even the unseen can be known through its influence. Let that thought settle gently as you prepare for rest. The universe may be vast and mysterious, but it is also coherent, traceable, and quietly illuminated by the methods we use to understand it. Future dark matter mapping efforts promise even greater detail. The upcoming Virasi-Rubin Observatory, with its wide-field imaging capabilities, will scan large portions of the sky repeatedly over a decade. Its data will allow scientists to measure weak gravitational lensing with unprecedented accuracy. By detecting subtle shifts in the shapes of billions of galaxies, the Rubin Observatory will help refine our understanding of how dark matter is distributed across cosmic time. These observations will Another promising development comes from space-based observatories. Missions like Euclid and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies with precise redshift measurements and shape information. The absence of atmospheric turbulence allows these telescopes to capture cleaner, sharper images, improving the accuracy of lensing measurements. Euclid, for example, will provide detailed maps of dark matter across more than a third of the sky, offering insights into the struct. Beyond traditional surveys, some researchers are exploring novel methods for mapping dark matter. One approach involves using fast radio bursts, brief, bright pulses of radio waves from distant cosmic sources. As these bursts travel through space, they interact with intervening matter in ways that may provide clues about the distribution of both ordinary and dark matter. While still in early development, these techniques hint at the creativity scientists bring to the challenge of studying the unseen universe. These advances in observational astronomy will gradually transform our understanding of dark matter. Each new survey adds resolution, depth, and context to the invisible structures shaping the universe. The cosmic web, once merely a theoretical prediction, is now mapped with increasing clarity. Its filaments, voids, and clusters reveal a universe in constant motion, guided by the quiet hand of gravity. For someone preparing for rest, there is comfort in knowing that even the unseen follows coherent, predictable patterns. The universe may be vast, but it is not. Even as the scientific community pushes forward, dark matter mapping remains a deeply human pursuit. It reflects our desire to know not only what is visible, but also what lies beneath appearances. The act of interpreting distortions in distant galaxies, or subtle shifts in the cosmic microwave background, requires patience and curiosity, traits that mirror our own inner explorations. Just as astronomers map the unseen universe, we too map our own thoughts, impressions, and intuitions. The process is gradual, gentle, and filled with discovery. As you relax into the quiet of the evening, imagine the universe laid out before you as a vast and delicate structure. The visible parts shimmer like stars on a calm lake, but beneath the surface lies a deeper network of invisible currents. These currents, dark matter, guide the formation of galaxies, shape the flow of cosmic events. In this hidden structure, there is both mystery and reassurance. Even without seeing it directly, we can understand it, map it, and learn from it. In the end, mapping the invisible universe is about more than tracing mass. It is about understanding the deeper forces that govern cosmic structure. Dark matter maps reveal how galaxies are connected, how clusters grow, and how the universe evolves across billions of years. They remind us that even the faintest signals, tiny distortions in a galaxy's shape, or subtle imprints in ancient radiation, carry information about the largest structures in existence. By piecing together these delicate clues, astronomers create a picture that transcends what the eyes can see. And in that process, there is a gentle reminder that discovery often comes from patience, stillness, and a willingness to follow the quietest traces of truth. Chapter 5. The Early Universe and Dark Matter Seeds. The early universe was extraordinarily smooth, filled with a hot, dense plasma where light and matter were intertwined. Yet within this seemingly uniform expanse existed tiny fluctuations, subtle differences in density that would eventually grow into galaxies, clusters, and the cosmic web. These faint variations were the seeds of structure, and dark matter was the first component of the universe capable of responding to them. For someone easing into a quiet state of mind, this chapter offers a calming purse. During the first few 100,000 years after the Big Bang, the cosmos behaved like a tightly coupled fluid. Photons collided constantly with electrons, preventing ordinary matter from collapsing under gravity. Any region that became slightly denser was quickly pushed back by radiation pressure, causing oscillations similar to sound waves. These are known as baryon acoustic oscillations, and they left an imprint on the distribution of matter that we can still observe today. But during this era, dark M, this difference between baryons and dark matter, meant that dark matter could begin to collapse into overdense regions long before ordinary matter was able to follow. These early dark matter clumps, though modest at first, created gravitational wells that grew deeper over time. They were the seeds of structure, natural gathering points that would later attract gas, form stars, and eventually become galaxies. Without dark matter initiating this process, the universe would have expanded too rapidly for order. A key turning point in cosmic history occurred around 380,000 years after the Big Bang, during the epoch known as recombination. At this moment, the temperature of the universe dropped enough for electrons and protons. For the first time, photons were able to travel freely through space rather than scattering repeatedly. This release of photons created the cosmic microwave background, CMB, a faint glow that still fills the sky today. The CMB provides a snapshot of the universe. The CMB does more than reveal the temperature of the early plasma. It encodes the distribution of density fluctuations across the young universe. By analysing these fluctuations, cosmologists can determine how much ordinary matter, and dark energy existed at that time. The patterns are unmistakable. Dark matter was already acting as the gravitational scaffolding of the cosmos. Without it, the fluctuations seen in the CMB would not match the structures observed in the universe today. This consi. After recombination, the universe entered a long, quiet era often called the Dark Ages. With no stars yet formed, the cosmos was dark except for the faint. During this time, dark matter continued its slow, gravitational collapse, deepening the wells that ordinary matter would eventually fall into. Gas cooled gradually, accumulating in regions where dark matter had already gathered. Only when these regions reached sufficient density did the first stars form, illuminating the universe. Simulations of cosmic evolution help visualize this process with remarkable clarity. Starting from the initial fluctuations mapped by the CMB, the simulations let dark matter evolve under gravity for hundreds of millions of years. Filaments, clusters, and voids begin to appear, forming the cosmic web. Ordinary matter flows into the densest regions, eventually igniting the first stars. The consistency between these simulations and observational data is one of the most compelling pieces of evidence that one subtle effect shaping the early. Because baryons were strongly influenced by photon pressure before recombination, they retained a residual motion relative to the already settling dark matter. This mismatch slightly delayed the collapse of baryons into smaller dark matter halos. Although the effect is small, it refined the timing of early structure formation and remains an active area of research. It demonstrates dark matter's inability to radiate energy also influenced the structure of halos during this period. Unlike baryonic matter, which cools by emitting photons, dark matter retains its kinetic energy. As a result, dark matter halos form smooth, extended structures rather than compact, rapidly collapsing ones. Ordinary matter settles into the centers of these halos, forming disks, bulges, and eventually star clusters. This natural division of roles, dark matter shaping the broad gravitational landscape and bar. Even today, astronomers study high redshift galaxies to better understand the Observations from the James Webb Space Telescope reveal galaxies forming surprisingly early, some just a few 100 million years after the Big Bang. Their existence reinforces the idea that dark matter seeds provided the necessary gravitational environment for rapid star formation. Without dark matter's early influence, these galaxies would not have formed so quickly or so coherently. The fact that we can reflecting on this sequence of events offers a soothing perspective. The universe began in near uniformity, yet from that quiet beginning, dark matter nurtured the first structures with patience and subtlety. Small differences grew into vast cosmic patterns. In these early seeds lies a lesson. Profound developments often start with subtle, nearly imperceptible variations. Whether in cosmic evolution or personal growth, the gentle accumulation of influence over time can shape everything that follows. As we continue exploring the early universe, it becomes clear that dark matter's role was not only foundational, but also remarkably consistent. Every stage of structure formation, from the growth of initial overdensities to the emergence of the first galaxies, was guided by the gravitational landscape carved out by dark matter. This landscape was not static. It evolved as the universe expanded and as structures merged. Small halos combined to form larger ones, creating an intricate hierarchy of gravitational environments. The earlier stars formed in the densest pockets of this hierarchy, where baryons could collapse rapidly once the dark matter wells deepened enough. These stars, massive and short-lived, produced the first heavy elements through nuclear fusion and supernova explosions. Their brilliant but brief lives were the beginning of chemical complexity in the universe. The chemical enrichment caused by these first stars had lasting consequences. When they exploded, they seeded their environments with elements like carbon, oxygen, and iron, enabling later generations of stars to form more efficiently. But even these dramatic events occurred within the gravitational confines established by dark matter. The location, density, and clustering of early star-forming regions were determined by how dark matter clumps had grown since the Big Bang. Thus, the earliest chemical processes in the cosmos were indirectly shaped by the dark matter seeds that formed long before the first atoms cooled. Another critical phase in early cosmic history was ionization. As the first stars and galaxies formed, they emitted ultraviolet radiation capable of ionizing the neutral hydrogen that filled the universe after recombination. This radiation gradually transformed the cosmos from a neutral state back into an ionized one. The timing and uniformity of reionization depended heavily on the distribution of early galaxies, which in turn depended on the distribution of dark matter. Regions with higher concentrations of dark matter hosted more early galaxies, accelerating reionization locally. In contrast, regions with fewer dark matter seeds experienced delays. This patchwork process left subtle signatures that astronomers are still unraveling today. Modern simulations incorporate reionization, early star formation, and dark matter physics to produce some of the most accurate models of the young universe ever created. These models reveal how sensitive cosmic evolution is to initial conditions. A slight change in the amount or behavior of dark matter would lead to vastly different outcomes. If dark matter interacted more strongly with radiation, the early plasma would have behaved differently. If dark matter were warm instead of cold, moving faster in the early universe, small-scale structure would have been suppressed, delaying galaxy formation. Each hypothetical variation demonstrates how finely tuned the early universe appears when viewed through the lens of modern cosmology. Observations of distant quasars also shed light on early dark matter seeds. Quasars are supermassive black holes, that formed surprisingly early in cosmic history, some within the first billion years. Their rapid growth requires dense environments rich in gas, environments that could only exist in regions where dark matter halos had already grown significantly. The existence of these early quasars provides indirect evidence that dark matter seeds formed efficiently and quickly after recombination. On smaller scales, the interplay between dark matter and baryons becomes even more intricate. As gas falls into dark matter halos, it can cool and condense, but feedback processes, such as radiation pressure, stellar winds, and supernova explosions, can temporarily push gas back out. This cycling of matter affects how galaxies grow and can even influence the inner structure of dark matter halos. Some models suggest that repeated bursts of star formation can heat dark matter through gravitational interactions, softening the dense central cusps predicted by simple simulations. This interaction between luminous matter and dark matter highlights the complexity of galaxy formation while preserving the overarching influence of early dark matter seeds. In recent years, astronomers have begun using 21 centimeter hydrogen absorption signals to probe the era before the first stars fully illuminated the cosmos. Although still in its early stages, this method has the potential to directly trace the influence of dark matter on structure formation long before galaxies became visible. As instruments improve, 21 centimeter cosmology may become one of the most powerful tools for studying the universe's earlier seeds. As we step back and consider the early universe as a whole, a striking pattern emerges. The cosmos grew from simplicity to complexity in a smooth and continuous flow. Dark matter, silent and unreactive, provided the gravitational architecture that made this transition possible. It formed the first wells into which baryons could fall, it set the stage for the first stars, and it guided the emergence of galaxies long before light filled the universe. Its influence can be found in every structure we observe today, from dwarf galaxies to massive clusters. The universe did not rush towards structure, it eased into it gradually, driven by the quiet pull of invisible matter. From tiny fluctuations, hardly more than whispers in the early plasma, grew the vast cosmic web. The same forces that shaped the first billion years continue to shape the cosmos now, maintaining a gentle continuity across unimaginable spans of time. For someone drifting towards sleep, this continuity can feel grounding, like the steady rhythm of a breath or the calm rise and fall of distant waves. Today, we continue to discover new details about these ancient seeds using ever more sophisticated tools. The James Webb Space Telescope, deep-field galaxy surveys, and upcoming missions promise to reveal structures even closer to the cosmic dawn. Each new observation enriches our understanding of how dark matter nurtured the early universe. And while many mysteries remain, especially regarding the true nature of dark matter, the story of cosmic seeds reminds us that not knowing everything does not diminish the beauty of what we do know. Instead, the unknown adds depth to the quiet wonder of the night sky. As you settle deeper into rest, imagine floating above the early universe, watching the first ripples of structure appear. See the faint light of the earlier stars flicker to life within dark matter wells that formed long before them. Picture the gentle evolution of filaments stretching across space, connecting regions that would one day become clusters of galaxies. In this unfolding tapestry, dark matter is the invisible thread guiding every pattern. With that image in mind, allow your thoughts to soften and drift, trusting in the quiet forces that shape both the cosmos and the moments of rest that carry you into sleep. Chapter 6: Dark Matter and the Birth of Galaxies. The birth of galaxies is one of the most graceful transformations in cosmic history. It begins not with light, but with gravity, specifically the gravity of dark matter. Long before the first stars illuminated the young universe, dark matter halos were already growing, deepening, and preparing the gravitational landscapes that galaxies would one day fill. In many ways, galaxies are the visible expressions of structures shaped primarily by invisible matter. Understanding how this process unfolds is not only, as the universe expanded after the Big Bang, the earliest dark matter halos formed around tiny overdensities, small regions where the density of matter was slightly higher than average. These halos grew through gravitational attraction, gradually pulling in more dark matter, and although the halos themselves were still invisible, they began exerting a profound influence on the distribution of ordinary matter. When the epoch of recombination freed photons from matter, baryonic gas was finally able to respond to gravity without being resisted by radiation pressure. Gas began to cool and fall into the dark matter wells. This was a slow, graceful descent, spread out across millions of years. The behavior of this early gas was governed by its ability to shed heat. As the gas cooled, it lost pressure support, allowing it to collapse even further into the deepest parts of each dark matter halo. In many ways, the first true galaxies emerged during the cosmic dawn, approximately 200 to 400 million years after the Big Bang. These early galaxies were small, irregular, and chaotic compared to the grand spiral and elliptical structures we see today. Their formation was driven by the delicate interplay between cooling gas, dark matter halos, and the first episodes of star formation. Without dark matter halos to stabilize the environment, the gas would have dispersed too quickly for stars to form in significant number. Once the first stars ignited, they began to transform their environments. Their intense radiation heated nearby gas, preventing further collapse in some regions, while supernova explosions disrupted and stirred the interstellar medium. These feedback processes shaped the growth of early galaxies, regulating how quickly they could accumulate new material. Yet through all this turbulence, the dark matter halo remained a steady, stabilizing force. Its gravitational pull kept the galaxy from dispersing even. The shape of a galaxy is closely tied to the properties of its host halo. Spiral galaxies, with their elegant rotating disks, typically form in halos with significant angular momentum. As gas collapses into such a halo, it retains some of its initial rotational motion. Over time, this motion causes the gas to flatten into a disk, where stars form in organized rotating patterns. The development of spiral arms, though shaped by complex gravitational interactions, ultimately traces back to the halo's angular. Elliptical galaxies tell a different story. These massive, rounded systems often arise from mergers, collisions between galaxies that scramble their stars and gas. When two halos merge, the resulting gravitational interactions can disrupt disks and mix stellar populations into smooth, elliptical distributions. The dark matter halos involved in these mergers grow larger and more structured through each collision, accumulating the histories of many smaller systems. This hierarchical growth is a hallmark of dark matter not only shaped where galaxies form vast cosmic voids. Large regions with few or no galaxies exist because dark matter seeds were distributed unevenly across the early universe. Regions with fewer seeds developed fewer halos, and therefore fewer galaxies. These voids form some of the most tranquil environments in the cosmos, vast stretches of space where gravity's influence is faint and galaxies are sparse. Their existence highlights how profoundly dark matters. Another important factor in galaxy formation is the cooling time of baryonic gas compared to the growth time of dark matter halos. In massive halos, gas can shock heat to extremely high temperatures, slowing its ability to cool and collapse. This can limit star formation, producing galaxies with extended hot atmospheres that glow in X-rays. In smaller halos, the gas cools more efficiently, forming stars more quickly. The balance between these processes helps determine whether a galaxy becomes a... Observations with modern telescopes, particularly the James Webb Space Telescope, have revealed galaxies forming much earlier than expected. Some of these galaxies appear surprisingly massive within just a few 100 million years of the Big Bang. Their rapid growth can only be explained by dense, well-developed dark matter halos that formed quickly after recombination. These halos acted as gravitational funnels, channeling gas into concentrated regions where stars could form at remarkable rates. Simulations of galaxy formation reinforce this picture. Starting with the initial conditions measured from the cosmic microwave background, cosmologists evolve the universe forward using advanced numerical models. In these simulations, dark matter halos form first, followed by the gradual cooling of baryons, the ignition of stars, and the turbulent evolution of galaxies through mergers and interactions. The resulting structures resemble the galaxies observed in deep surveys, providing strong evidence that, as galaxies grow, their interactions with dark matter remain deeply intertwined. The distribution of dark matter within a halo affects the shapes of orbits, the growth of central bulges, and the stability of disks. In turn, galactic processes like supernova-driven winds can push baryonic matter outward, subtly altering the dark matter distribution through gravitational feedback. This ongoing exchange keeps halos and galaxies in a delicate dance, each influencing the other over billions of years. Reflecting on the birth of galaxies offers a peaceful reminder of how structure emerges from subtle beginnings. A galaxy is not the product of sudden change, but of gradual accumulation, a long, quiet process shaped by gravity, cooling, and time. Dark matter provides the framework, the invisible architecture on which the luminous parts of the universe. For someone drifting towards sleep, this story is a gentle one, a universe where complexity grows slowly, guided by unseen forces that act with pat. In the next chapters, we will explore how galaxies continue to evolve within their dark matter halos, how clusters form from the merging of many galaxies, and how the cosmic web connects all structures across vast distances. For now, it is enough to imagine a newborn galaxy settling into its halo, shining softly for the first time as dark matter holds it steady. In this quiet partnership between light and shadow, the universe reveals its delicate balance, an interplay that continues even now across the end. Another key stage in the birth of galaxies involves the cooling of atomic hydrogen, the most abundant element in the universe. As gas collects inside dark matter halos, it gradually cools through processes such as collisional excitation and the efficiency of this cooling determines how quickly the first dense clouds can collapse to form stars. In smaller halos, hydrogen can cool efficiently through atomic transitions, enabling early bursts of star formation. In very small halos, however, the gas cannot cool effectively, preventing galaxies from forming at all. This threshold helps explain why the population of galaxies exhibits a natural cutoff in size and brightness. Many halos contain too little mass to cool their gas, creating a large population of dark halos with no stars. The influence of dark matter can also be seen in how galaxies acquire their angular momentum. As halos grow by accreting matter from the cosmic web, they experience gravitational torques from nearby structures. These torques generate rotation, which is later inherited by the baryonic gas that falls into the halo. When the gas cools and settles, it forms rotating disks that eventually become spiral galaxies. This process explains why spiral galaxies tend to align their rotational axes with the large-scale filaments surrounding them. Their orientation reflects the gravitational history of their halos, shaped long before the visible galaxy existed. Galaxy mergers also played a prominent role during the universe's first few billion years. Small proto-galaxies frequently collided, sometimes merging smoothly, and other times violently transforming one another. These encounters helped build the diversity of galaxy types we see today. In each merger, the halos themselves also merged, deepening their gravitational wells and changing the internal structure of the combined system. The stars within the merging galaxies often found themselves on new orbits, mixing together to create the smooth shapes characteristic of elliptical galaxies. The dark matter halo acted as both the stage and the stabilizing force during these transformative events, ensuring that galaxies remained gravitationally bound even amid dramatic rearrangements. Modern observations reveal that some of the earliest galaxies were surprisingly clumpy, with star-forming regions scattered across irregular shapes. These clumps form because early gas-rich disks were highly turbulent, stirred by rapid accretion and frequent mergers. The dark matter halos surrounding these galaxies acted as containers, preventing the systems from dispersing despite their chaotic appearances. Without the gravitational envelope of the halo, the turbulence of early star formation would have torn the galaxies apart. Instead, the halos provided a buffer, allowing galaxies to evolve gradually into the more stable structures observed today. Another important factor is the influence of feedback from black holes, especially the supermassive black holes found at galactic centers. These black holes can release enormous amounts of energy as they accrete matter, heating or expelling gas from the surrounding region. This feedback regulates star formation, particularly in massive galaxies where gas densities are high. Yet even in these extreme environments, dark matter halos continue to dictate the overarching structure. The halo's mass determines how much gas can be retained after a feedback event, influencing whether a galaxy remains active in star formation or becomes dormant. Thus, the invisible halo influences even the most energetic processes occurring at galactic centers. Galaxy clusters, massive structures containing hundreds or thousands of galaxies, are another example of dark matter's essential role. Clusters form at the nodes of the cosmic web. As galaxies fall into clusters, they interact through processes such as tidal stripping, ram pressure stripping, and gravitational harassment. Despite these disruptive forces, the dark matter halo of the cluster maintains the coherence of the system as a whole. The galaxies orbit within the cluster's gravitational potential, held together by dark matter that outweighs the stars by a factor of roughly 10. Over cosmic time, dark matter halos continue to shape galactic evolution through subtle gravitational effects. Halos can develop triaxial shapes, elongated or flattened structures, rather than perfect spheres. These shapes affect the orbits of stars, influencing the formation of bars, rings, and spiral arms. Halos can also interact with one another through tidal forces, creating streams of stars and gas that reveal the hidden structure of the dark matter distribution. In this way, dark matter acts like an artist working behind the scenes, shaping the galaxy's visible features without ever appearing directly. As we reflect on the birth of galaxies, it becomes clear that their existence is inseparable from the dark matter halos that cradle them. Galaxies are not isolated phenomena. They are expressions of deeper gravitational structures, shaped by forces that began acting long before the first star flickered. In this understanding, there is a sense of continuity and quiet reassurance. The universe grew its luminous structures with patience, building on foundations laid in darkness, guided by gentle gravitational pulls that never demanded attention, yet shaped everything that would follow. For someone drifting into rest, this slow emergence of order from the faintest beginnings can feel deeply calming. It reminds us that growth is often gradual, that complexity comes from subtle accumulation, and that the most influential forces can be the quietest ones. Dark matter, though unseen, played the central role in one of the universe's greatest transformations, the birth of galaxies. And just as galaxies formed in the shelter of these invisible halos, we too grow in the presence of unseen supports, patterns, memories, and steady influences that guide us even when we cannot name them directly. As we move forward into the next chapters, we will follow galaxies as they evolve, cluster, and merge across cosmic time. For now, let the story of their beginnings settle gently in your thoughts, a reminder that even in vast darkness, the seeds of light and structure are always taking shape, preparing the universe for the beauty that follows. Chapter 7: Galactic Evolution. Inside dark matter. Halo's galaxies do not evolve in isolation, nor do they drift aimlessly through the universe without guidance. Their histories, from quiet star formation to turbulent mergers, unfold inside the vast gravitational cocoons provided by dark matter halos. These halos determine how galaxies grow, how they rotate, how they interact, and even how long star formation persists. In many ways, a galaxy's visible form is simply the luminous trace of an invisible structure that shapes nearly every aspect of its evolution. From the moment the first galaxies took shape, dark matter halos became the stage on which their stories would play out. The early halos were small and rapidly growing, collecting gas with surprising efficiency. As the halos deepened, they created These disks were fragile in the early universe, frequently disturbed by mergers and inflows, yet the halos surrounding them helped maintain coherence during even the most chaotic events. One of the most influential aspects of halo-driven evolution is the steady accretion of gas from the cosmic web. Filaments funnel cold gas directly into halos, allowing galaxies to form stars for billions of years. This smooth inflow is a quiet yet profoundly important process, setting the tempo for a galaxy's growth. Galaxies embedded in dense filamentary environments tend to grow faster, while those in quieter regions evolve more slowly. The invisible scaffolding of dark matter determines the richness of these environments, guiding the frequency and intensity of the material that sustains star formation. Over time, these mergers can trigger brilliant starbursts, reshape galactic structures, or even fuel the growth of supermassive black holes at galactic centers. Yet through all this transformation, the halo remains the dominant mass component. absorbing the kinetic energy of merging galaxies and keeping the evolving system gravitationally bound. Even the most dramatic collisions, disks shredded, stars flung into long tidal streams, are ultimately governed by the deep stabilizing influence of the halo. At smaller scales, the internal structure of halos influences how stars form and how they orbit. Halos are not smooth spheres. They contain subhalos, remnants of past mergers, which contribute to subtle irregularities in the gravitational field. These irregularities can shape the orbits of stars, producing faint ripples and streams in the galactic halo. In some galaxies, these stellar streams are visible like soft, ghostly ribbons, remnants of smaller systems absorbed over billions of years. Each stream is a quiet reminder of how halo-driven evolution leaves lasting imprints on visible matter. Dark matter halos also regulate how galaxies form their central bulges. As disks evolve, gravitational instabilities, often enhanced by the shape of the halo, can funnel gas toward the center, where it forms dense stellar populations. These processes give rise to classical bulges in some galaxies, while in others, a more gradual redistribution of stars produces peanut-shaped or bar-like structures. The shape of the halo influences which of these evolutionary pathways dominates. Another key element of galactic evolution is feedback, the return of energy and material from stars and black holes into the surrounding gas. Supernova explosions can active galactic nuclei, powered by supermassive black holes, can inject enormous amounts of energy, sometimes halting star formation entirely. Yet even these powerful events are moderated by the halo's gravitational pull. A massive halo can retain gas despite intense feedback, allowing the galaxy to recover and continue forming stars. Smaller halos, however, may lose substantial amounts of gas, leading to long periods of quiescence or even permanent dormancy. Environmental effects also shape how galaxies evolve within halos. Galaxies inside clusters experience tidal forces, high-speed encounters, and interactions with hot intracluster gas. Processes such as ram pressure stripping can remove gas from galaxy disks, shutting down star formation. Still, throughout all these transformations, it is the cluster's enormous even when a galaxy loses its gas or is distorted by tidal interactions, it remains bound to the cluster through the halo's deep gravitational well. As galaxies age, their stellar populations evolve, changing the way they shine. Halos influence this process by modulating gas inflows, merger rates, and star formation histories. Large halos tend to host galaxies that grow steadily over time, while small halos often experience bursts of star formation followed by long pauses. This variety of growth pathways explains why galaxies display such diversity today. Spirals with rich disks of young stars, ellipticals filled with older stellar populations, and dwarf galaxies with irregular, chaotic histories. Behind all these forms lies the quiet yet persistent influence of dark matter. Modern simulations illustrate the beauty of this interaction. When cosmologists model the growth of halos and galaxies over billions of years, they see disks forming, merging, fragmenting, and reforming inside their halos. They see long tidal tails stretching across hundreds of thousands of light years, and they see newly formed stars lighting up pockets of gas shaped by the halo's potential. The agreement between these simulations and observations is striking, further reinforcing the idea that galaxy evolution cannot be understood without accounting for the unseen matter that guides it. Galactic evolution continues even today. The Milky Way, for example, is currently interacting with several satellite galaxies, including the Sagittarius dwarf galaxy. As these satellites fall into our halo, they leave trails of stars behind, creating arcs and streams that ripple through the outer regions of our galaxy. In a few billion years, the Milky Way will merge with the Andromeda Galaxy, a dramatic but ultimately orderly event governed primarily by the enormous halos surrounding both galaxies. The resulting galaxy will be larger, rounder, and more massive, shaped once again by the invisible forces beneath its surface. Reflecting on all of this reveals a comforting truth. The visible universe is only the surface of a deeper structure. Galaxies glow with starlight, but they grow, evolve, and persist because they are held by the quiet gravity of dark matter halos. For someone drifting toward rest, the story of galactic evolution offers a gentle reminder that the most profound influences in life can be subtle and unseen. Just as galaxies flourish within their halos, we too evolve within environments shaped by forces we may not always notice. Relationships. As this chapter closes, imagine a galaxy gliding through its halo, its stars swirling in harmonious orbits, its gas flowing in from intergalactic filaments, and its history written in faint streams of starlight. See how calmly it moves within its invisible envelope, guided by gravity that has acted for billions of years. Let this image settle your thoughts as you prepare for rest. A universe evolving slowly, patiently, and beautifully, shaped by what cannot be seen yet felt across the largest scales of space and time. Another dimension of galactic evolution inside dark matter halos involves the slow migration of stars over cosmic time. Even in a seemingly stable galaxy, stars gradually drift outward or inward due to subtle gravitational interactions with gas clouds. Young stars formed in the bright spiral arms may eventually wander into quieter outer regions, while older stars born closer to the center may drift outward into the halo. This blending helps explain why galaxies often show a gradual change in stellar ages rather than sharp boundaries. The dark matter halo's gravitational field provides the stable environment that makes such long-term migration possible, holding the galaxy's structure steady while its stars slowly reposition themselves over billions of years. Gas flows also play a crucial role in shaping galaxies inside their halos. While gas can stream inward along filaments to fuel star formation, it can also be pushed outward by stellar winds, supernova explosions, and black hole activity. This outflow and inflow cycle contributes to the self-regulation of galaxies. In dwarf galaxies, for example, even moderate stellar feedback can eject gas far beyond the visible disk, temporarily stalling star formation. In more massive galaxies, the halo's deep gravitational well pulls the gas back, allowing it to cool and eventually form new stars. This constant recycling of material gives galaxies a rhythmic, pulsing quality, a long, slow breathing pattern guided by the halo's unyielding grip. Dark matter halos also influence the chemical evolution of galaxies. As stars live and die, they enrich the surrounding gas with heavier elements such as carbon, oxygen, and iron. These elements gradually accumulate, shaping the next generation of stars and altering the colour and brightness of the galaxy. Yet how quickly this enrichment spreads, and how evenly it is distributed, depends on the halo's shape and depth. In halos with strong gravitational potentials, enriched gas remains close to the galaxy, enabling rapid chemical evolution. In smaller halos, enriched material may be blown far into intergalactic space, slowing the buildup of heavy elements. Thus, the chemical maturity of a galaxy is directly linked to the mass of the halo in which it resides. Environmental quenching provides another striking example of halo-driven evolution. Galaxies that fall into massive clusters often lose their gas due to interactions with hot intra-cluster plasma. This process, called ram pressure stripping, can remove gas so efficiently that star formation stops within a relatively short time. Even galaxies that retain some gas may experience strangulation, where their supply of fresh inflowing gas is cut off by the cluster's massive halo. Without replenishment, their remaining gas is slowly consumed or heated, eventually halting star formation. In this way, a galaxy's long-term brightness and colour can be predicted simply by knowing the environment of its halo. One of the most visually compelling signatures of halo-driven evolution is the presence of stellar shells and ripples around galaxies. These delicate structures form when a smaller galaxy falls into a larger halo on a radial orbit. As the smaller system is disrupted, its stars spread out along extended loops, creating faint arcs that wrap around the host galaxy like layers of gauze. These shells are long-lived because the host halo's gravity preserves their orbits, allowing astronomers to reconstruct ancient mergers. Each shell or ripple is a fossilized record of a past interaction, preserved by the silent stability of the surrounding dark matter halo. Looking ahead, the future evolution of galaxies remains tightly connected to the growth of their halos. As the universe expands and the supply of cold gas dwindles, galaxies will gradually exhaust their fuel for star formation. Their halos, however, will continue to merge and grow, gathering the remnants of smaller structures. In the distant future, most galaxies in the local group will coalesce into a single massive system. The stars within it will drift in wide, slow orbits, illuminated occasionally by new bursts of star formation triggered by mergers or accretion events. Even as the visible universe becomes quieter, the halos will persist, shaping cosmic evolution long after star formation fades. In contemplating this long arc of evolution, one finds a peaceful symmetry. Galaxies begin, grow, transform, and merge within the steady embrace of their halos. The galaxies may shine brightly, flicker, or fade, but the halos endure, shaping their paths with quiet strength. For someone easing into rest, this cosmic steadiness can feel like a reassuring anchor, a reminder that even as visible forms shift and change, deeper structures persist, guiding the flow of time and light. Chapter 8: Dark Matter in Galaxy Clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies, enormous reservoirs of hot gas, and, most importantly, vast quantities of dark matter. They are cosmic cities, formed at the intersections of the great filaments of the cosmic web. In these clusters, the influence of dark matter becomes unmistakable. Its gravitational presence shapes the motions of galaxies, the temperature of the intracluster gas, and even the path of light travelling from far beyond the cluster's boundaries. To understand clusters is to see dark matter acting on its grandest stage, guiding the evolution of structures that span millions of light years. Unlike individual galaxies, which form within isolated halos, galaxy clusters grow through a continuous process of accretion and mergers. Small groups fall inward, feeding the cluster with fresh galaxies' gas. This ongoing growth gives clusters their complex internal structure: swirling subclusters, elongated shapes, and streams of material drawn from the surrounding cosmic web. Yet beneath all this complexity lies a deep, extended halo of dark matter that binds the entire system together. The visible matter in clusters, stars, galaxies, and hot gas accounts for only a small fraction of their total mass. Most of the gravitational glue is dark. One of the key tools for studying dark matter in clusters is the measurement of galaxy velocities. Galaxies within a cluster move at extraordinary speeds, often exceeding 1,000 kilometers per second. If only the visible matter were present, these galaxies would escape the cluster's gravity, but they remain bound, held in place by the deep gravitational potential well carved. These measurements consistently reveal far more mass than can be accounted for by stars or gas alone, providing compelling evidence for dark matter on the largest scales. Another crucial component of galaxy clusters is the intracluster medium, ICM, a vast reservoir of superheated gas that fills the space between galaxies. This gas glows in X-rays, reaching temperatures of tens of millions of degrees. Its temperature and distribution reveal the depth of the cluster's gravitational potential. Only an enormous amount of mass, far more than what is visible, could heat the gas to such extreme levels. Dark matter provides this mass, forming the underlying structure that holds the ICM in place. The pressure of this hot gas helps shape the cluster, but it is ultimately dark matter that defines the cluster's overall gravitational architecture. Gravitational lensing offers perhaps the most direct method of mapping dark matter in clusters. Light from distant galaxies travelling through a cluster is deflected by the cluster's mass, creating distorted shapes, arcs, and in some cases, multiple images of the same background object. By analysing these distortions, astronomers can reconstruct the distribution of mass, both visible and invisible, within the cluster. These maps reveal dense concentrations of dark matter surrounding galaxies, extended halos enveloping the cluster, and filamentary structures that connect the cluster to the broader cosmic web. Lensing shows the dark matter directly through its gravitational signature, painting a detailed picture of how mass is arranged in these colossal systems. One of the most important discoveries in cluster cosmology comes from studying cluster collisions. Unlike galaxies, which contain relatively little gas, clusters contain enormous quantities of hot plasma that interact when two clusters collide. The gas slows down, shocks, and piles up due to pressure forces. Dark matter, by contrast, passes through largely undisturbed, affected only by gravity. This separation between gas and dark matter becomes a powerful probe of the cluster's true mass distribution. The most famous example is the bullet cluster, where the visible gas lags behind the dark matter after a collision. Gravitational lensing reveals that the mass peaks align with the dark matter, not the gas. This provides some of the clearest evidence that dark matter behaves differently from normal matter. Beyond the bullet cluster, several other merging clusters exhibit similar behavior. The gas slows down, the dark matter does not. These systems collectively form one of the strongest observational cases for the existence of a non-baryonic form of matter. If modified gravity alone were responsible for the observed motions, it would be extremely difficult to explain why the mass distribution aligns with the galaxies rather than with the gas, the component that contains most of the visible mass in a cluster. Instead, the simplest explanation is that dark matter is a real, distinct component that does not interact with radiation or pressure forces. Substructure within clusters provides additional insights. Clusters are not smooth, static systems. They are dynamically evolving environments shaped by constant infill. This means clusters contain subhalos, smaller concentrations of dark matter that correspond to individual galaxies or galaxy groups. Simulations predict that these subhalos should survive for billions of years, slowly orbiting the cluster center. Observations confirm this. Gravitational lensing maps show small pockets of mass around cluster galaxies, matching the predicted locations of subhalos. These structures reveal the hierarchical nature of dark matter clustering, small halos merging into larger ones, which eventually become the massive clusters we observe today. The growth of galaxy clusters over time also provides clues about dark matter's properties. If dark matter interacted more strongly, if it exchanged energy or momentum with itself, clusters would appear smoother and rounder than they do. Instead, clusters display the clumpy, filamentary structure expected for cold, collisionless dark matter. These features place tight constraints on dark matter models, ruling out many alternatives that predict more interactions or warmer particle speeds. The shape, density profiles, and substructure of clusters together reinforce these enormous systems sit deep within the cluster's dark matter well and grow through mergers with smaller galaxies. Their vast stellar halos often extend hundreds of thousands of light-years, blending seamlessly into the surrounding intra-cluster light. This diffuse glow comes from stars that have been stripped from galaxies during interactions. The distribution of intracluster light provides additional evidence for the cluster's dark matter structure, tracing the orbits of stars within the gravitational potential of the halo. On even larger scales, clusters are connected by cosmic filaments, highways of dark matter and gas that feed material into the cluster over billions of years. These filaments contain galaxies moving along elongated paths, gradually falling into the cluster's center. Clusters located at the junctions of many filaments grow rapidly, while those with fewer connections evolve more slowly. The position of a cluster within the cosmic web is therefore a key factor in determining its history and future growth. Dark matter defines these filaments, creating the channels through which matter flows across the universe. For someone drifting toward rest, the structure of galaxy clusters offers a calming sense of scale and stability. Clusters evolve over billions of years through gentle accumulation punctuated by occasional dramatic mergers. Through all these processes, dark matter remains the quiet architect of structure, shaping everything from the motion of galaxies to the glow of hot gas. Its presence is steady and pervasive, a gravitational foundation beneath the visible universe. The study of galaxy clusters also allows cosmologists to measure fundamental parameters of the universe. Because clusters are so massive, their abundance and distribution are sensitive to the nature of dark matter, the properties of dark energy, and the geometry of spacetime itself. Counting clusters at different epochs provides a cosmic census that helps constrain how quickly structures formed. These measurements complement other cosmic probes, such as the cosmic microwave background and large-scale galaxy surveys. Together, they form a coherent picture of a universe shaped overwhelmingly by dark matter and dark energy. As you drift deeper into relaxation, imagine the quiet majesty of a galaxy cluster. Hundreds of galaxies orbiting within a vast halo of unseen matter, threads of dark filaments connecting the cluster to distant regions, and the faint X-ray glow of hot gas filling the space between galaxies. All of these structures move in harmony, guided by the steady pull of dark matter. This gravitational choreography has been unfolding for billions of years, shaping the largest structures in the cosmos with patience and quiet precision. The clusters embedded in dense regions of the cosmic web tend to accrete new material more rapidly. These bustling environments are filled with infalling groups, faint subhalos, and streams of gas drawn along the filaments. In contrast, clusters located in quieter regions experience slower growth, allowing their internal structures to relax and settle over long timescales. The rate of accretion affects everything from the temperature of the intracluster gas to the distribution of galaxies within the cluster. Dark matter governs this process by defining the gravitational landscape through which material flows. At the heart of many galaxy clusters lies a phenomenon known as cool core structure. While the intracluster gas is extremely hot overall, the central regions of some clusters show evidence of cooling. Radiative processes cause the gas to lose energy, potentially allowing it to condense and form new stars near the cluster center. However, this cooling is often counteracted by energetic feedback from central supermassive black holes. These black holes release jets and bubbles of energetic plasma, which reheat the gas and prevent runaway cooling. The balance between cooling and heating shapes the central galaxy and influences the surrounding halo. Without the deep gravitational well provided by dark matter, these processes would unfold very differently. Cluster mergers are among the most dramatic events in the universe. When two clusters collide, the amount of energy released is enormous, surpassed only by the Big Bang itself. Shock waves ripple through the intracluster gas, heating it to even higher temperatures. Dark matter halos pass through each other with minimal friction, continuing on their trajectories even as the gas slows. These collisions create observable features such as shock fronts, radio halos, and turbulent flows. Yet beneath all the apparent chaos, gravity gradually pulls the merged system back together, forming a single, more massive cluster. This ongoing cycle of collision and relaxation demonstrates how clusters grow through cosmic time. Some of the most fascinating discoveries in cluster research come from systems undergoing multiple mergers. These triple merger clusters display complex patterns of dark matter distribution, with several sub-halos converging on the central region. Gravitational lensing reveals elongated structures and multiple peaks in the mass distribution, showing how dark matter retains information about past interactions. These systems challenge simulations to reproduce intricate merger histories, providing a powerful test of the cold dark matter model. Despite their complexity, the underlying physics remains grounded in the gravitational behavior of dark matter. Beyond individual clusters, cosmologists study cluster populations to understand the evolution of the universe as a whole. The number of massive clusters observed at different redshifts provides insight into the growth rate of cosmic structure. If dark matter were warm or strongly interacting, the formation of clusters would be delayed or suppressed. Instead, observations reveal a population of clusters consistent with cold, collisionless dark matter. Their abundance, internal structure, and distribution across the cosmic web all support this interpretation. Clusters serve as cosmic milestones, marking key stages in the universe's growth. Future observatories will deepen our understanding of galaxy clusters and their dark matter halos. The Euclid mission, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory will map galaxy distributions and lensing. These surveys will allow astronomers to trace the evolution of clusters across cosmic time, measuring how dark matter assembled into increasingly larger structures. High-resolution X-ray telescopes will probe the intracluster medium, revealing the interplay between gas dynamics and gravitational forces. Together, these instruments will refine our understanding of dark matter's behavior on the largest scales. Chapter 9. The Cosmic Web and Dark Matter's Grand Architecture. Across the vastness of the universe, the cosmic web stretches like a subtle tapestry, an immense structure of filaments, nodes, and voids sculpted primarily by dark matter. It is the largest pattern in existence, a quiet network woven across billions of light years. Every galaxy, every cluster, and every filament owes its position to the gravitational scaffold. In this chapter, We explore the shape and scale of that cosmic architecture, moving gently through its structures as if floating in a calm intergalactic stream. The cosmic web began as faint ripples in the young universe, tiny differences in density that dark matter magnified through gravity. Over billions of years, as dark matter drifted toward regions slightly heavier than their surroundings, filaments began to emerge. These long thread-like structures connected dense nodes, each destined to become a galaxy cluster. Between the filaments lay vast voids, regions with so little matter that they expanded faster than the average universe, stretching into enormous cosmic cavities. As dark matter collapsed into these structures, ordinary matter followed. Gravity pulled gas into the filaments, where it cooled and condensed, giving rise to galaxies. The filaments became rivers of matter, feeding clusters located at the intersections of many filaments, grew into some of the most massive structures in the universe. Even now, they continue to accrete matter from the web, deepening the cosmic architecture. Simulations offer breathtaking views of this network. Starting with the distribution of dark matter shortly after recombination, cosmologists evolved the universe forward to reveal a web-like structure spanning hundreds of millions of parsecs. These simulations show filaments twisting and merging, voids expanding, and clusters lighting up like brilliant knots along the cosmic strands. When astronomers compare these simulations with actual large-scale sky surveys, the match is remarkable. The observed clustering of galaxies, the sizes of voids, and the distribution of filaments all align with predictions made by dark matter-driven models. One of the defining features of the cosmic web is its scale. Filaments can stretch hundreds of millions of light-years across while remaining only a few million light-years thick. Clusters at their nodes can contain thousands of galaxies. Voids between filaments can span enormous regions with almost no galaxies at all. And yet, even in these empty places, dark matter is present, thinly distributed, quiet, but still part of the web's structure. Dark matter's behavior determines the stability of this architecture. Because dark matter does not interact through electric or nuclear forces, its evolution is slow and graceful. It moves under the influence of gravity alone, drifting toward the densest regions and stretching the filaments as the universe expands. This lack of interaction is what allows the cosmic web to remain coherent over billions of years. If dark matter collided or scattered like gas, the web would have a very different shape, smoothed out, less filamentary, and far less capable of forming the complex structures we observe today. The cosmic web also influences the orientation and evolution of galaxies. Observations show that galaxies forming inside filaments tend to align their rotation axes with the direction of the filament. This alignment reflects the flow of matter along the filament, revealing how galaxies inherit their angular momentum from the surrounding dark matter structure. In clusters, however, the environment becomes more turbulent, and galaxy orientations become more random due to interactions and mergers. This contrast between filamentary order and cluster chaos highlights the subtle but pervasive influence of dark matter on galactic evolution. Void regions, those vast underdense expanses, provide another window into dark matter's role. Though they contain very few galaxies, voids are essential components of the cosmic web. Their rapid expansion stretches the surrounding filaments and amplifies the contrast between overdense and underdense regions. Studying the shapes and distributions of voids helps astronomers understand the growth rate of cosmic structure, providing key insights into both dark matter and dark energy. In many ways, voids are just as important as clusters for revealing the universe's history. At the intersections of massive filaments lie superclusters, enormous structures composed of many galaxy clusters bound loosely together by gravity. Our own Milky Way resides in the outskirts of the Laniakea supercluster, a region connected by long filaments of galaxies stretching across hundreds over billions of years. Accelerated expansion driven by dark energy will pull superclusters apart, leaving clusters isolated within the cosmic ocean. The transition from small-scale structure to the cosmic web reveals a remarkable harmony in the universe's evolution. On small scales, dark matter forms halos that host galaxies. On medium scales, halos merge to build groups and clusters. On the larger scales, these clusters connect through the cosmic web. Each level reflects the same basic physics, gravity pulling matter into denser regions. Yet the patterns grow increasingly intricate as the scale increases, creating a universe rich in structure but unified in its fundamental behavior. One of the most extraordinary tools for studying the cosmic web is weak gravitational lensing. Unlike strong lensing, which produces dramatic arcs and multiple images, these distortions, when measured across millions of galaxies, reveal the underlying distribution of dark matter. Weak lensing surveys, such as those conducted by the Hypersuprime CAM, and upcoming missions like Euclid, allow astronomers to map the cosmic web directly. These maps confirm the filamentary patterns predicted by simulations, providing some of the clearest evidence that dark matter forms the universe's structural backbone. Another method comes from studying the Lyman alpha forest, absorption features in the spectra of distant quasars. As light from these quasars travels through intergalactic gas in the cosmic web, it is absorbed at specific wavelengths by hydrogen atoms. The pattern of absorption reveals the density of gas along the line of sight, which in turn traces the distribution of dark matter. By analysing thousands of quasar spectra, astronomers can reconstruct three-dimensional maps of the cosmic web stretching billions of light-years into the past. The cosmic web is not static. It continues to evolve even now. Filaments grow thicker as they draw in mass, clusters grow heavier as they merge, and voids expand as matter flows toward denser regions. This slow evolution creates a sense of cosmic breathing, an expansion and redistribution of mass driven by dark matter's gravitational pull. Over the next tens of billions of years, the web will continue to stretch and thin as dark energy accelerates the universe's expansion. Eventually, the largest filaments will break apart and clusters will become isolated islands in an ever-growing cosmic sea. This future may feel distant and abstract, yet it adds a gentle sense of melancholy to the beauty of the cosmic web. Structures that took billions of years to form will slowly drift out of reach. But in this slow unfolding, there is also peace. The universe is not rushing toward change. It drifts, shifts, dark matter guides this process, shaping the web with a patience far beyond human timescales. For someone drifting towards sleep, imagining the cosmic web can be deeply soothing. Picture yourself floating along a vast filament, surrounded by soft glows from distant galaxies. Ahead lies a cluster, glowing faintly with X-ray light from its hot gas. Behind you stretches a quiet void, open and expansive. The web is serene at this scale, its features immense but gentle, shaped by invisible forces that never hurry. In this stillness, the universe feels both grand and deeply calming. As we close this chapter, consider how the cosmic web embodies the essence of dark matter's influence. It is a structure invisible to the eyes yet revealed through its quiet gravitational pull. It is a network that connects galaxies and clusters across unimaginable distances, yet its formation depends on the time. It is both delicate and immense, both stable and evolving. And through its patterns we glimpse the profound order that runs beneath the visible universe. Dark matter may be unseen, but in the cosmic web, its presence becomes unmistakable. Every filament, every node, every void speaks to its influence. And as you gently drift into rest, you can imagine yourself moving through this quiet architecture, a peaceful voyager in a universe shaped by the soft gravity of the invisible. The cosmic web also influences how matter flows across the universe on timescales far longer than a human lifetime. Filaments act like bridges between clusters, guiding the trajectories of galaxies as they migrate toward deeper potential wells. Even isolated galaxies feel the faint tug of nearby filaments, drifting slowly over billions of years. This continuous motion is subtle, almost imperceptible in the short term, yet over cosmic timescales, it produces graceful, large-scale rearrangements of these slow drifts help maintain the coherence of the web, preventing it from collapsing into a uniform haze despite the relentless expansion of the universe. Dark matter ensures that structure persists, anchoring mass in place while allowing gentle movement along gravitational contours. Within filaments, galaxies experience a unique evolutionary environment. The density of matter is higher than in the field, but lower than in clusters, creating a gentle middle ground. Gas can flow into galaxies more steadily, fueling ongoing star formation. Interactions are more common than in isolation, but far less violent than in cluster cores. This balanced environment often produces galaxies with extended disks and well-regulated star formation. The filament itself acts as a stabilizing influence, its dark matter backbone shaping the paths along which gas and galaxies travel. The flow of material along these threads contributes to a sense of directionality in the cosmic web, as if the universe itself encourages matter to trace elegant lines across space. Superclusters, though loosely bound, provide another scale on which the cosmic web reveals its grandeur. These enormous structures are not isolated bodies but sprawling regions where filaments converge and diverge. The dark matter within these superclusters gives rise to complex gravitational landscapes, gentle slopes, broad basins, and extended ridges of mass. Galaxies and clusters migrate through this terrain over billions of years, following paths shaped by dark matter that stretch far beyond what optical light alone can show. Instruments that measure galaxy velocities and gravitational lensing reveal these landscapes with increasing detail, offering a glimpse into the slow choreography that governs the largest patterns in the universe. As observations improve, astronomers are beginning to map the cosmic web in 3 dimensions with remarkable accuracy. Techniques such as redshift surveys, weak lensing tomography, and quasar absorption analysis allow scientists to reconstruct the positions of filaments and voids across cosmic time. These reconstructions reveal that the web is not uniform. Its threads twist, merge, and sometimes dissolve, only to reform elsewhere as dark matter redistributes itself. This dynamism is subtle but constant, a gentle evolution that continues even now. Each newly mapped filament adds another brushstroke to our understanding of the cosmic canvas. Reflecting on the cosmic web invites a sense of calm, as its scale dwarfs any individual concern. The structures we see today emerge from tiny fluctuations billions of years ago, nurtured by filaments and voids stretch across unimaginable distances, yet they form patterns that feel surprisingly organic, almost like the branching of rivers, the spreading of roots, or the delicate networks found within living organisms. This resemblance is coincidental but comforting, reminding us that structure and harmony can emerge at every scale of nature. The cosmic web is not chaotic, it is balanced, connected, and enduring.